to the capillaries, to the venules, to the veins, and back to the heart. But if we look at these arteries in cross-section, one of the things that strikes us is that around the inside of the artery is a layer of endothelial cells. So if this is going to be an artery, or even an arteriole, it's lined with endothelial cells. So this is meant to be the endothelial cell lining. Remember, we said wherever we go in the cardiovascular system, whether we're in the chambers or in the vessels, we have a lining of endothelial cells. Those endothelial cells sit on a basal lamina. And typically there's a fairly robust layer of connective tissue here. And then what we find is around the entire circumference of the arteriole is smooth muscle. Again, the smooth muscle is under autonomic control. The smooth muscle will have receptors called alpha-1 adrenergic receptors. These two work through a G-protein coupled receptor. But this G-protein coupled receptor, in response to epinephrine or norepinephrine, causes smooth muscle. Contraction. So let's think about this for a little bit and think about what's going on here. We have this series of tubes, and on the arterial side, and even down all the way to the arterioles, and down all the way up into the aorta, they're surrounded by smooth muscle. That smooth muscle now is under control. So now what happens here? Let's run this back a little bit farther and have some more branches. So that if we have smooth muscle around, say, this branch and this branch. Oh, this is badly drawn. Let's see if I can get my slides up. Oh, it's preparing Windows now. It's another period of time. Okay. Let me erase that and try again. Sorry about this. So let's imagine we have these series of arterioles. And they are then feeding into a series of, I better put it in green. into a series of capillaries. So if these are the capillaries, and this is smooth muscle here, we can now shunt blood in different directions. We can shunt the blood to different capillary beds. By regulation of the smooth muscle contraction. Let me show you some slides. And then what I'll do is I will mount the lecture from last year too. So here's the vascular slide that I wanted to show you. Is it going to come on? Yes. So what they're trying to describe here is, and what I was trying to describe on the board so badly, is that we have these arterioles, and these will branch and branch and branch, all these different arterioles, which will then finally branch into the capillaries. All of these arterioles are surrounded by smooth muscle. So let's take, for example, smooth muscle around the fourth order and third order arterioles. We clamp these down. All of these other second order and first order arterioles will also have capillaries linked to them. So by doing this, by using the smooth muscle and contracting them here, we'll increase the resistance to flow through this tube by reducing the radius. And then in that way, we're going to shunt blood through the other tubes. It's just a means of shunting blood. And the way this is working is if, for example, you go out on a cold day and you want to retain heat, what you begin doing is you begin closing down the blood vessels going out to your skin. And so you now reduce blood flow to the skin, and in this way your skin turns white, but you've now retained heat by moving that blood to your core regions of your organs. We do this all the time. We have this arrangement of the smooth muscle being innervated by the alpha subunit, innervated by the sympathetic branch of the autonomic nervous system. So what does that mean, and how does that work? Let's put this in the backboard. So remember that flow is equal to delta P pi r to the fourth divided by 8 eta L. Well, we said that the flow then is proportional to the radius to the fourth power. This means by small by making small changes in the radius, we can change the flow through a set of tubes. And we can now shut blood to different places by choosing which smooth muscles to activate to reduce the radius. So all we're saying here is that smooth muscle contraction of arterial smooth muscle affects flow. And that it's the autonomic nervous system innervating that smooth muscle which now can affect flow. And it does that through its effect on the radius. And because of Poiseuille's law, we now have big effects on the flow by small changes in the radius. And we use this trick throughout the vascular system through innervation of the arterial smooth muscle. The other piece I want to show you here is it? Was this one? I've showed this one before. This shows a couple of things. So this is showing the branching of the system. It's showing how we go from aorta to large arteries to smaller arteries to arterioles to capillaries to venules to small veins and large veins and back to the vena cava. Now, what we used this for before was to show the effect of the pressure in the aorta to drive the blood through the coronary blood vessels. What I want to show you here is that as this blood moves out into the aorta, the large arteries, and the smaller arteries, that you'll see that the pressure's dropping. Remember we said early on that the return blood flow to the heart, whether it's to the right side or the left side, that return blood flow is always a low pressure return. And the reason it's a low pressure return is that as the blood flows through these tubes, that energy that was first imparted to the blood by the contraction of the left ventricle, that energy is dissipated through friction along the walls. So that means as we move from the single tube of the aorta out into all these other tubes, and particularly when we start getting to the arterioles, we see a tremendous drop in pressure because of all of that branching. Now by the time we get to the capillaries, we're down around 30 millimeters of mercury. Because of the enormous surface area of the capillaries, we further drop the pressure. So that by the time we get back to the vena cava, the pressures here that are propelling the blood back into the right side of the heart are in terms of 5 to 10 millimeters of mercury. We start out in this series of tubes here with 110 or 120 millimeters of mercury. And because of the branching of the aorta into these large arteries, it'll even go up into some of the large arteries. But then as the frictional effects of the fluid moving along the walls begin to take effect, then the pressures begin to drop. And as they begin to drop, we see it's a precipitous drop here in the arterioles, and then a pretty good sized drop in the capillaries, some in the venules. But by the time we get down back to the vena cava, we have a low pressure return. But you'll notice we still have a fair amount of pressure here in the capillaries. And that's what I want to do now. Are there any questions on how we can regulate the flow of blood through the tubes by using smooth muscle? Okay, let's then spend the last few minutes here, mercifully. talking about what's going on at the level of the capillaries. So hold on to the idea from that slide that there's a certain amount of pressure, probably 40, 50 millimeters of mercury, that was generated by the contraction of the left ventricle. And we're going to think now about the pressures that are against the walls of those capillaries. And we'll take this panel and we'll label it as something known as hemodynamics. Hemodynamics in the capillary beds. Now, if we imagine one of these capillaries, and we imagine the blood flowing through here. I won't put the erythrocytes in. What we see is that there's a pressure. The pressure will be in the neighborhood of 30 to maybe as much as 50 millimeters of mercury. The source of that pressure, the source of the pressure is from the contraction of the left ventricle. This pressure of 30 to 50 millimeters of mercury is said to be the hydrostatic pressure. This is a mechanical pressure. Produced by ventricular, I should say left, ventricular contraction. This is just a mechanical force. Sometimes it's hard for people to get their head around this. But remember, this is a closed system. There's no place to relieve the pressure. The pressure is generated in the left ventricle. The pressure goes out into the aorta and into the arteries, and that's the pressure we saw in that last slide. But because of the friction of the fluid against the walls, that pressure dissipates. And by the time we get down into the capillaries, we're down to 30 to 50 millimeters of mercury, but yet still there is a sizable pressure against the walls of these vessels. This is a hydrostatic pressure. Now, there are these small gaps between the adjacent endothelial cells. What this means is that the hydrostatic pressure has the capacity to move small molecules like ions, but especially water, out across and between these endothelial cells. But one of the characteristics of these gaps is they're small, and they fail to allow the movement of proteins across the endothelium. Now we'll see here when we talk about blood here, which I'd hope to do today, we'll probably have to get to it on Monday, that a sizable proportion, about 55% of the blood is plasma. The plasma is a protein solution. So what's going to happen is we have these blood proteins. And the blood proteins now have a molecular weight of about 40,000. Well, at molecular weight 40,000, these are too big to move through the narrow gaps. So they're stuck. So water leaves, but protein remains behind. So we have a hydrostatic pressure that moves water out of the capillary into the extracellular space. But there's another pressure here. There's a pressure because of the proteins. There's an osmotic pressure. To return water to the capillary. So now we have two forces. We have an osmotic force inward and a hydrostatic force outward. They're close, they're not far off. But the hydrostatic force is greater than the osmotic force. These are pressures. We have a hydrostatic pressure and an osmotic pressure. We therefore have a delta P. Whenever you have a delta P, we have a flow. Now, the flows we've talked about before are the flows moving through the vessels, but now we have a flow from the inside of the tube to the outside of the tube. We're now going to be bathing the tissues in fluid that's leaving the blood vascular compartment. Only a very, very tiny fraction of the fluid leaves the blood vascular compartment. But some does leave, and it generates something known as lymph. We'll come back to lymph next week when we talk about the blood and the lymphatic systems, and we'll see that there are special tubes that are now going to be used to carry that lymph back into the blood vascular compartment. But for now, just recognize that this idea of hemodynamics derives from the pressure that we generated in the left ventricle, the pressure against the walls of the capillary. But in addition to that hydrostatic pressure, because we can't move the proteins, we have an osmotic pressure returning the water. But the hydrostatic pressure is a little bit bigger than the osmotic pressure, so there's a net flow of fluid out of the tubes into the extracellular space. So any questions to there? So it's mercifully come to an end. So what I'll do is I'll see if I can mount the links to the ones from last year where we actually had some slides and I think was a better lecture. Thanks.